Let me share my screen first. Uh, can you please respond if my screen is visible or not? Hello. Hello. Is my screen visible to everybody? You can just write in the chat box, right? Oh, okay. Fine then. So let's start with sample questions for week 3. Yeah. So the first question that is given is so the multiplicity of HHL planes in the cubic system is. So it's given that the family of planes is HHL and multiplicity you have to find out. So there's a trick to this problem. I mean, this combination is this is 3C2 number of combinations, right? It can be H, so it can be H, H, L, it can be H, L, H, and it can be L, H, H, right? Now, among them, you have to bring in the negatives also. I mean the bars. So you can have 1 bar, 2 bars, and 3 bars, right? So this is 3C1 plus 3C2 plus 3C3. So among them, 1 will be barred, 2 will be barred, and all 3 will be barred. So same goes for this too. And for this, right? Right. So this is 3 into 3C1 plus 3C2 plus 3C3 plus you have already 3 combination, that is HH and LH and LHH, means no indices are part, right? So there's no negative index, so for that 3. So this is 3 into 3 plus 3 plus, so this is 1 plus 3, this is 24. So the multiplicity of HHL planes in the cubic system is 24. So there can be 24 number of candidates in this family of HHL planes. Alright, so the right answer is 24 number of. Right. So I hope you didn't find any problem with this first question. And if you in between find a problem, or if you have any queries, please write in the chat box, or please unmute yourself and ask. Right? Let me just check my recording. Yes. Okay. Okay. So which of the following is or are true for Miller indices of crystallographic planes and directions? So the first option that is given is that all the parallel equidistant planes must have different Miller indices. This is not true because they'll have same Miller indices, right? Just there'll be multiple of that, right? A plane parallel to one of the coordinate axes has an intercept of infinity on that axis. So this is true because if you draw your coordinate axis, so if this is the case, so some plane that is parallel to z axis will give you this. Okay. So this is an intercept of infinity on the z axis, and so a plane parallel to one of the coordinate axes has an intercept of infinity on that axis. That statement is correct. If the Miller indices of two planes are 1, 2, and 2, 4, 4, the planes are parallel to each other. We can check it's not, because 1 to 1, if you double it, then it would have been planes, but they are parallel to each other. But in this case, it's not. So the third option is incorrect. And let's check the fourth answer. Fourth option: all the planes and directions in a cubic system are orthogonal to each other. As we already have been learning throughout the lecture in this week, that for a cubic system, if this is HKL, the directions will be given by HKL. So they're orthogonal to each other, and this is only applicable for cubic system. For tetragonal system, as you have noticed, this is not the case necessarily. So the two correct answers are: a plane parallel to one of the coordinate axes has an intercept of infinity on that axis. Correct? And all the planes and directions in a cubic system are orthogonal to each other. Right? So this is it. So what are the Miller indices of the plane that makes intercepts of 1, 2, and 2 angstrom on the x, y, and z crystallographic axis respectively of an orthorhombic crystal with A is to B is to C equals 3 is to 2 is to 1. So let me first check if there's a question. Okay. So you people are able to see my screen and see the problems you worked out, right? Okay. Anyway. So first of all, you have to have the intercepts in terms of the uh, uh, crystallographic axis respectively. So that would be, so 1 sorry, red. So 1 comma 2 comma 2 angstrom, right? And A times B C is 3 is 2 is 2. So this is now Miller indices. The we have to have that intercept in terms of the this crystallographic axis. So that will be 1 by 3, that is 2 by 2, and 2 by 1. All right. Now we have to do the reciprocal. Right? So just to find the Miller indices, intercepts, right? Reciprocal would give you 3, 1, half. Reduction plus the integer, that is, we multiply it by 2, so that will fetch you 6, 2, and 1. So your Miller indices are 6, 2. So the correct answer is 6, 2, and okay. So what we did is simply we found out the intercepts on the x, y, and z axis respectively for this orthorhombic crystal where A naught equals B naught equals C. So first we found out the intercepts, then we did the reciprocal, and then we found reduced it by multiplying it with the shortest integer, so that the HKL are integers. All right. Now, which of the following are the Miller indices of the non-parallel body diagonals of a? All right. So let me just okay, check it between. Yes, yes, yes. So okay. So if I draw a cube, so this is it. If I draw a cube, so to find the Miller indices of the body diagonals of a cube, right? So this is A, this is B, this is C, this is D, this is E, F, G, H. All right. So now, if you take A as the origin, then you have to reach at G, right? So if A is the origin, then the indices would be, this is 1, this is of course this is your, this is E, this is Y, this is X, right? So in this we have to go to 1, 1, and 1, right? So for A to G diagonal, it is 1, 1, 1, right? For B, if B is the origin, then you have to go at H, right? So you have to go 1 in this direction, plus 1 in Y, minus 1 in X, and plus 1 in Z. So for B, it is minus 1 X, I mean 1 in Y and 1 in Z, and this is equivalent to 1 bar, 1, 1. All right. Now for C, you have to go to E, right? Now you have to go in C, you have to go in negative in X, negative in Y, and positive in Z. So 1 bar, 1 bar, and 1, right? So this is it. And for D, you have to go to F, right? So for D, you have to go to D, you have to go this minus 1, positive 1, and positive on the X side. So 1, 1 bar, 1. All right. Now for E, you have to go to C, right? So if E is the origin, in that case, E would be given by positive positive F, positive Y, and negative positive X, positive Y, and negative C. So in that case, 1, 1 bar. For f, you have to write, you have to go to D, right? So if this is the case, f, so this is 1 bar, 1 bar. Alright. For G, you have to go to A, right? So for G, you have to go to H, Y, and H, Y, this side and this side, right? So 1 bar, right? And H. For H, you have to go to P, right? So positive in X, negative in Y, and negative in C, right? All right. So positive in X, negative in Y, and negative in yes. So the bunch that goes with this is 1 1 1, 1 bar 1 1, 1 1 bar 1, and 1 1 1 bar. All right. So 1 1 1 bar is a body diagonal that are non-parallel. So first one is obviously an answer, and you can of course do take a bar of that, complementary of that, and say that C is also the answer, which is already included in our case. All right. So for A, you have to go to 1 1 1 and 1, A to G, right? For B, you have to go to -1 1 and 1. All right. For C, you have to go to -1 1, right? And for D, you have to go to -1 -1 and 1. So in this case, you have to carry forward and see that these are the following Miller indices with non-parallel body diagonals of a cube, and these are the pairs, right? So yeah, so we have got the answer. Now moving on to next question. So I hope you are getting the answers. So yeah. So the angle between the directions 1 to 3 and 1 minus 1 1 in cubic system is. So these are the direction cosines, as you can obviously notice. So angle between them will be given by, so cos theta is equals, so this is 1 2 3 and 1 minus 1 1, right? So this is u1 v1 w1 u2 v2 w2. So u1 u2 plus v1 v2 plus w1 w2 by under u1 square plus v1 square plus w1 square plus in times u2 square plus u square plus w square, right? So this is the case, and now this is 1 1 plus 2 into minus 1 plus 3 into 1 divided by root under 1 squared plus 2 squared plus 3 squared times 1 squared plus or minus 1 squared 1 squared, right? So this is basically 2 by root 1 squared. This is 9, this is 13, and this is 14 times this is, right? So this will give you the answer, I guess. Yes. So if you do this, so theta is equals cos inverse 2 by 14 times 3, right? This will give you the answer as 72 degree. Right? Simple and straightforward. So the answer is 72 degree. Right? This was pretty simple. Now to the next question, which of the following is or are true for crystalline solids? So among them, they have long range periodicity. They maintain a periodic nature for long distances, right? So that would be one answer. They give sharp diffraction patterns. This is also correct. They have varying bond energy in atoms. This is not true because they maintain a periodicity. The atoms are mainly bonded by secondary bonding. This is also not true because they are bonded by the metallic bond. Alright. So this is not secondary bonding. So they have long range periodicity and they give sharp diffraction patterns. Okay. Now the seventh question. In a hexagonal system, a plane with Miller indices 1 to 3 in 3-digit convention could be converted into following Miller-Brevis indices using 4-digit convention. All right. So for planes, for planes from 3-digit convention from HKL is appearance HKI and L, where I equals minus H plus K. Okay, so it's simple to write that it is, yeah. So in 4-digit convention, it can be written as from 1 to 3. We have 1 to 3. So H and K remains same and minus of 3, right? So minus of 1 plus 2. So that is 3 part and L remains same as above. So this is the answer. So straightforward, very we have already learned from the lectures. So 1 to 3 bar 3 is the answer. Okay. Yeah. Please feel free to unmute yourself and ask questions in between if you have any queries, or you can also write in the chat box, right? In hexagonal system, Miller indices of a direction. Now for direction, for directions, U, V, W. 3-digit convention is converted to 4-digit convention. U, V, T, W. T, the T is your, as it is, T is minus of U plus V, and capital U is 2U plus V, and capital V is 2V plus U. Okay, so now it is, we are given 2 bar 1 bar 1. Okay, so minus 2 is 2U plus V, minus 1 is 2V plus U. So multiply the first with 2, so minus 4 is equal to 4U plus 2V, and just subtract this with this, so that will give you 3U is equal to minus 3. Therefore, U is equal to minus 1. Right? So if U is minus 1, then with minus 1, if U is minus 1, then this U is minus 1, then V is 0. Alright, so minus 1, 0, and minus of minus 1 plus 0, that is 1, and W stays as it is. So the final answer would be 1 bar 0 1. This is your U, this is your V, this is your T, this is your W. So A is minus U plus V, right? So this is it. So the right answer is 1 part 0 1 1. Right? This is the correct answer. So what is the coordination number of atoms in case of close packed monatomic structures, right? So coordination number of atoms in, so let me just insert some pictures. So first of all, yeah, so this is the picture. So if this is your atom is for close packed structure, if the atom sits at this, so there are 3 neighboring atoms, right? So that would be your 1, that is 2, and that is 3. So I am talking about this, right? Now starting another, the second stage, the second layer, that would be given by this, right? So that is, let me just okay. So this is it. So let me just paste in the end. So this is your first, right? So this is your first. Sorry for this. So what you basically do is, this is 1, this is 2, and this is 3, right? Now you insert another layer. It's another layer, which is the second layer, that will fetch you so this is it. So now this atom already it has 3, and this is 4, this is 5, this is 6, 7, 8, 9. All right, another layer on top of it would give you another layer on top of it will already give you your 10, 11, 12, right? So for the close packed structure, you have 12 neighboring atoms, and coordination number is, as I talked about in the last class, is the number of coordination number of neighboring atoms, nearest neighboring atoms. So that will give you your number of 12. So coordination number of atoms. So coordination number of atoms. So coordination number of atoms in case of close packed monatomic structure is 12, which I already showed. So the next question is the atomic positions in face-centered cubic unit cell. All right. So let me just draw a face-centered cubic unit cell. So this is your cube. This is your cube. This is your yes. This is your yes. So now you have the atoms over here. Here, right? As we already saw in the last class. Just to differentiate, these are all same atoms, but just to differentiate, I am putting the atoms on the faces as this, as this, as this, as this. So if you consider as this as origin, consider this as origin. Let's say for going to this, for the nearest neighbors, you have to, this is okay. So this is the coordinate axis. This is the coordinate axis. This is E. This is x, this is y. So this this will give you half half and 0. This is 0 0 0. This is 0. Now for this phase, this will give you half 0 half, right, this one, and the nearest, this will be given by this, right, and this will be given by 0 half half. So, and this, the entire cubic system, the face centered cubic, will be the reflection or the mirror image of these three nearest neighbors. So the atomic positions in face centered cubic unit cell are 0 0 0, half half 0, half 0 half, and 0 half half. So this is the correct answer. All right. So we're almost at the end. Which of the following best describes the hexagonal close packed structure? So insert, we have the picture with us. Pardon me, I didn't post it earlier. Okay, this is wrong. Now, yes, now this is it, right? So this is the hexagonal close packed structure. We have the 6 corners, atoms at the 6 corners, at the middle, and also at the base plane also. And in between them, there are 3 atoms which sits at the middle of these atoms, right? So consider the primitive unit cell, which is a simple tetragonal unit cell. In that case, you have, you have the motif as this, and this as the another motif. So primitive lattice with motif at 0 0 0, if you consider this as 0 0 0 0 0 0, all right. So in that case, you have to say that this is the unit cell. So this is that unit cell. This is that unit cell I'm talking about. So this is the unit cell I'm talking about, right? This is the unit cell I'm talking about. So in this case, 0 0 0, and staying at 0 0 0, we have to go to 1/3, 2/3 along this crystal axis. This is A1, this is A2, and this is A3, right? So in that case, you have to go to from this 1/3, this is 2/3, and this is half. So which of the following best describes the hexagonal close packed structure? This is primitive lattice with motif at 0 0 0 and 1/3, 2/3, and half, right? So this is this. So face centered cubic lattices, another problem. So this is what we need. So face centered cubic lattices, these are all, as we know that it will be all 1 1 1 planes. So close packed planes along 1 1 1, these are planes. So close packed along 1 1 planes, and close packed directions will be these directions, right? So this is your 1 and 1 and 0. So family of 1 1 0, right? And family of planes which is 1 1 1. So this is the direction of close packed structure, right? So this is 1 1 0 close packed direction family, right? So the answer would be close packed planes along 1 1 1 and close packed directions along 1 1 0, right? So this is close packed directions along 1 1 0. Okay, fine. Now the correct relation between the lattice parameter A and the atomic radius R in a body-centered cubic unit cell. So let me just draw a body-centered cubic unit cell. So if this is it, yes. Okay. So this will be, see, this will be this, this will be at this, this will be at this, 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 and this. So if at this body diagonal is touching, so in the middle there will be another, although I'm drawing it with different color, but don't consider it as a different atom, they are same atom and they are touching, right? So for the body diagonal, the length of the diagonal is uh, uh, that is your a squared plus a squared plus a squared, right, is equal to root 3a is your body diagonal, right? This is your body diagonal. All right, but so this is your body diagonal, so this is your body diagonal, okay, but it will consider only half of this sphere, a full of this sphere, and half of this sphere, half is outside, right? So this will consider as root 3a is half of this sphere, so half of this sphere radius plus 2r plus r and of this sphere, right? So this will give you your a is 4 by root 3 r. All right, so that will give you your 4 by the relation 4 by root 3 r. This is simple, this is very, very simple. And hexagonal close packed structure is described by the stacking sequence. Also want to show it with a picture. So this is hexagonal close packed. So this is close packed, right? So this is hexagonal close packed. So this is A, this is B layer, on top of it A B A B A B, and also it can also be yes, it can be A B A B A B, and it can also be B C B C B C layer of stacking. All right. So we are at the final question. So which of the following directions is or are common to the planes 1 1 1 and 1 1 1? So this is from the Y zone law. So this is Y zone law. So Y zone law, that is, you know, if this is H1 K1 L1 and H2 K2 L2 are two similar planes and they have the same directions, that is U V W. So in that case we'll have H1U plus K1V plus L1W is equal to 0, and H2U plus K2V plus L2W is equals 0. So invoking Cramer's rule, you can solve this in invoking Cramer's rule. Invoking Cramer's rule, you can solve this. So U is K1 L2 minus K2 L1. V is H1 L2 minus H2 L1, and W is H1 K2 minus H2 K1. And the places are given 1 1 1, 1 1 1, and 1 2 but 1, right? Okay, and 1 2 but 1. So U is 1 into 1 minus 1 into minus 2, right? This is 3. This is V is 1 into 1 yeah, minus 1. equals 0. So that is it. Let me just check. Yes, that is 0. And for W, it is 1 into 1 minus 1 into, sorry, that's incorrect. So that will give you 1 into minus 1 into 1. See. Alright. So what you have is 3, 0, 3 bar. Alright. But you can also write it as 1, 0, 1. And you can also write it as 1 bar, 0, just the part of it. Alright. Just the opposite direction. So from the plane you can have perpendiculars along two directions only, mutually along two directions, right? So 101 bar is 1 and 1 bar 0 is another, right? So B and C are the correct answers, right? So we are done with today's problems. Now if you can please ask questions, and if you have any queries, please ask. Okay then. So in that case, can we wrap this up? If you don't have any, can we end today's session then? Okay. 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 So I'll stop sharing.